This video is about the block that is moved up a ramp. So we will first read the statement together. A 4 kilogram block is pulled up a 6 meter long ramp with a force of 50 newtons. The block started from rest, that's an important fact, at the bottom of the ramp and arrived at the top with a speed of 7 meters per second. What is the work done by friction force acting between the block and the ramp? You are probably used to solve these kind of problems using forces and Newton's laws. However, in this question, there are two things that let us think that another option would be better. First, they give us not the acceleration, but actually the speed of the object. And the second thing is that we're not asking for the force, but we are rather asking for the friction, the work done by the friction force. So to approach this, instead of using Newton's second law and the sum of forces, we'll go straight away to calculating the work. But we know that we'll have to link the work done with the speed of the object. So in the end, we will need to use the fact that the work is equal to the change in kinetic energy. It's called the work energy theorem. We will be using this towards the end of the problem. The rest will all be about the work calculated for a constant force. And in that case, we know that the work is just equal to the scalar product between the force and the displacement done by the object, which can be rewritten as just the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the two. This angle is super important, all right? So if you have a force that is pointing in one direction and you have a displacement that is pointing in another direction, the angle that we're looking for is really the angle between these two vectors, and that's the one that is important. So now let's see how we can actually solve the problem. The first thing to do is to calculate the work done by each of the force, and to do this we first need to identify all the forces that are acting on the block. So here we really want to study what's happening on the block itself. So yes, indeed, we'll have a force that will be pointing up the incline. That will be the tension that is propagated through the string. But we also have the normal force that is pointing perpendicular to the incline, as well as the force due to gravity, pointing straight down as usual, and finally the force of friction. If the block is pulled upward, we expect that the force of friction will go against the motion, so we know that the force of friction will be down the incline. The easiest of these forces, the easiest force that we can use to calculate the work is indeed the work done by the normal force. This, as we saw in the previous slide, we can use the equation. It's just the normal force multiplied by the displacement times the cosine of the angle between the normal force and the displacement. It's a little bit complicated to calculate the normal force in here because we would need to decompose the force of gravity, but we don't need to do this because if you think about it, the displacement in here is up the incline, but the normal force is perpendicular to the incline. This means that we know that the angle between the two is in the right angle. So we know that theta, the angle between the normal and the displacement, is of 90 degrees. And since the cosine of 90 degrees is equal to 0, we know that the work done by the normal will be 0 joules, which is not surprising. That's the case anytime we have a force that is perpendicular to the displacement. Second force that I want to consider is the tension. Tension, again, is fairly simple. We have the tension, which is already given in the question. We know it will be 50 newtons times the displacement, which is given as well. And we need to find what is the angle between the two. Now we know that the displacement is up the incline, but we also know that the tension is up the incline as well. So the angle that we have between the two is actually of 0 degrees. Now we just need to add the numbers to make the calculations. So we have that the tension is equal to 50 newtons times the displacement of 6 meters times the cosine of 0 degrees. And once we put all of this together, we get 300 joules. Just note that this is a positive number, which makes sense since the tension in here is clearly providing energy to the block. So therefore we have positive work done. Then there's the work done by gravity. This one is slightly more difficult just because the angle is not as straightforward. So we'll have the force of gravity, mg, times the distance covered, times the cosine of the angle between the two. But that angle, okay, we have the displacement that is pointing up the incline, while FG is pointing straight down. So we need to figure out what is the angle that we have in here. That's what we're after. An easy way to see it is to realize that the horizontal line in here has an angle of 30 degrees with the incline. So therefore, if we add the 90 degrees between the horizontal and the vertical, we get a total of 120 degrees. So plugging this back in our equation, we have the mass, which is 4 kilograms, times g, 9.8 meters per second squared, times the displacement of 6 meters, and then we have to multiply again by the cosine of 120 degrees. If we do the math of all of that, we get 117.6 joules, but please note that this time we actually have a sign that is negative because the force of gravity is trying to slow down the block, so we get this negative force. And then the last force we have is the force due to friction. So if we calculate the work done by the force due to friction, we'll have again the same kind of thing. We'd have Fk times d times the cosine of the angle, and the angle this time will just be the angle between the force of friction and the displacement, and that angle, not surprisingly, will be equal to 180 degrees. So we won't need actually this fact to solve the question because it's already asking for the work done by friction. But if we were to find what is the friction force instead, that's how we would do it. So once we have all of these together, we can then think about how we can link it to the energy. So the work, as we said before, is equal to the change in kinetic energy. A change is always the final value minus the initial value. In this case, we know that the kinetic energy at the beginning is just equal to 0 since we know that the initial velocity was 0. And the final kinetic energy, we know, will be equal to 1/2 times the mass times the final velocity squared, which is just equal to 1/2 times the mass, 4 kilograms, times the final velocity, which is given at 7 meters per second. We square this last part, and once we do the math, you see that we have 4 divided by 2, that's 2, times 7 squared, that will give us 2 times 49, which is 98. And we can look at the units, kilograms times meters squared over second squared. This is a unit of energy, so we will get joules in here. So in the end, we know that this work in here, although I forgot to note it down, is actually the net work. It's the combination from all, the sum of all the contribution from all forces. So the net work we can also rewrite as the work done by the tension plus the work done by the normal plus the work done by the force of gravity plus finally the work done by friction. So in this case, the value that we're looking for is really the work done by friction. So we will isolate this one. And what we get is that since we know that the net work is equal also to the kinetic energy, we'll have that the work done by friction is equal to the net work minus the work done by the normal minus the work done by gravity minus the work done by the tension. The work done by the normal, that's an easy one as well. We found that this was just 0. So what we're left with is just the work done, the net work, which is equal to the 98 joules of the final kinetic energy, minus the work done by gravity. But remember, the work done by gravity was negative itself. It was minus 117.6 joules. So we have 2 negative in here, minus the 300 joules from the work done by the tension. So in the end, what we get once we do the math is that the work done by friction is equal to minus 84.4 joules. The negative sign in front makes sense because we know that the friction will try to slow down the block, and that's the answer we're looking for.